Imagine you type cute cat on sofa into a search bar and you get nothing back, zero results. But your database is full of cat pictures. The problem is that traditional search looks for the exact characters you typed. If your photo is labeled a kitten resting on a couch, the words don't match, so the computer says it doesn't exist. And that's crazy, right? Any human would say those two things mean the same thing. So, how do we teach a database to understand meaning instead of just letters? That's exactly what a vector database does, and by the end of this video, you'll understand how one works from the inside out. So let's start with the basics. A vector database is a database built for one job: storing lists of numbers that represent meaning and finding the ones that are closest to each other. That's really it. Three things. It stores those lists of numbers, it organizes them so searching is fast, and it answers the question, what's most similar to this? Everything else is detail. Now, where do those numbers come from? They come from something called an embedding model. Think of it as a translator. You give it a sentence, a photo, an audio clip, anything, and it hands you back a long list of decimal numbers. Something like 0.21 minus 0.31, 0.56, and so on. That list is called an embedding or a vector. And here's the magic part. The model doesn't just scramble your data into random numbers, it's been trained so that things which mean similar things get similar numbers. A cat on a sofa and a kitten on a couch come out looking almost identical. A car comes out looking completely different. Here's the part that makes it click. Think of those numbers as coordinates. Two numbers give you a point on a flat map. Three numbers give you a point in a room. Real embeddings use hundreds or thousands of numbers, so we can't picture it. But the idea doesn't change. Every piece of your data becomes a single point floating in space. And because similar meanings get similar numbers, related things land near each other. Cat, dog, and wolf cluster in one neighborhood. Apple, banana, and mango cluster somewhere else. Meaning has literally become geometry, and the number of coordinates depends on the model you pick. It might be 128, it might be 768, it might be over 3,000. More dimensions means more nuance and more storage. So now, searching becomes really simple. You take your question, cute cat on sofa, and you run it through the exact same embedding model. Same translator, same rules. Out comes one more point in that same space, that's your query point. And now, the database just asks, which stored points are nearest to this one? It grabs the closest few, ranks them, and hands them back. That's called a top K search, where K is just how many results you want. 3, 5, 50, you decide. And notice what happened. Not one word matched. It didn't need them to. But hold on. What does nearest actually mean when you're dealing with 1,000 numbers? Well, there are a few ways to measure it. The most popular one is Cosine similarity, which ignores how long the vectors are and only looks at the angle between them. Point in the same direction, you're similar. Point apart, you're not. Then there's Euclidean distance, which is the plain straight line between 2 points, just like measuring with a ruler. There's the dot product, which cares about direction and size together. And there's Manhattan distance, which adds up the steps you take along a grid, like walking city blocks. 4 different rulers. For text embeddings, Cosine similarity is the one you'll see almost everywhere. Okay, but here's the problem nobody warns you about. Comparing your query against every single stored vector works beautifully when you have 1,000 of them. Now try 10 million. Every search means 10 million comparisons, and your users are sitting there watching a spinner. Perfect accuracy, unusable speed. So vector databases do something clever. They stop looking for the perfect answer and start looking for a very good answer, very fast. This is called approximate nearest neighbor search. You give up maybe 2% accuracy, and in exchange, your search goes from nearly 2 seconds down to a handful of milliseconds. Nobody notices the 2%, everybody notices the 2 seconds. So how do they pull that off? The most common approach builds a graph in layers. The top layer is sparse, just a few points, spread far apart so you can cross the whole space in a couple of big jumps. Underneath it, more points. And at the bottom, everything. You enter at the top, jump toward whatever's closest, drop down a layer, jump again, and keep going until you're in the right neighborhood. It's like flying to the right country, then driving to the right city, then walking to the right street. A handful of hops instead of 10 million comparisons. There are other tricks too. One approach groups your vectors into clusters ahead of time and only searches the 2 or 3 clusters closest to your query, ignoring the rest entirely. Another one compresses each vector by chopping it into chunks and replacing each chunk with a short code, which can shrink your memory footprint by 20 or 30 times. And for truly enormous collections, in the billions, there are index designs that live on solid state drives instead of memory. Different tools, same trade-off every time: speed, accuracy, and memory. Pick two. Now, what does actually using one look like day to day? Honestly, it's about 5 commands. You insert a vector along with some metadata, like a category or a date. You search for the nearest neighbors to a query. You search with a filter so you only get results from, say, New York. You update the metadata on something, and you delete things you don't need. That's the whole surface area. If you've used any database before, you'll be productive in an afternoon. And the biggest reason teams reach for one right now is retrieval augmented generation, usually shortened to RAG. Here's the flow. A user asks a question. You turn that question into a vector. You search your vector database for the handful of document chunks that are most relevant. Then you hand those chunks to a language model and say, answer using this. That's how a chatbot answers questions about your company's internal documents without ever being trained on them. Same idea powers semantic search, recommendation engines, image and video search, duplicate detection, and spotting anomalies. As for which one to use, there's Pinecone if you want it fully managed, Weaviate, Milvus, and Qdrant if you want open source, Chroma if you want something lightweight to start with. There's a library called Phase from Meta if you want to build it yourself. And if you're already on Postgres, there's an extension called PG Vector that adds vector search to the database you're already running. Don't pick based on the logo. Pick based on how many vectors you have, how fast you need answers, whether you need metadata filtering, and what you're willing to spend. Just be honest about the trade-offs. You get incredibly fast similarity search, you handle high-dimensional data comfortably, and you scale to billions of items. But your results are approximate, not guaranteed perfect. High-dimensional vectors eat storage. Building the index costs real time and real compute. And this is not the tool for your bank transactions. Keep a normal database for that. So here's the one thing to remember. A vector database turns meaning into coordinates and turns similarity into a lookup. Embeddings go in, nearest neighbors come out, and it happens in milliseconds. That's the foundation underneath almost every AI product you've used this year. If this made it click for you, subscribe. We go this deep every week.